CMB.
My talk is based on a couple of published papers. And there are papers, work in progress, which I'll also discuss. Let me start with something which was summarized in the talk of Licia Verti, that standard cosmological model, so-called lambda CDM, is in good agreement with observations. And one can compare the situation with the standard model in particle physics in early 80s, when an essential agreement was observed. However, it required 20 or more years for a complete confirmation based on precision data of all but neutrino part of standard model, as everybody knows. Similarly, many features of standard cosmological model, which include inflation and current acceleration, may require many years of precision data for a complete confirmation. However, already now there are 6 parameters which describe well the WMAP 3 observations of about 2,000 points, and they agree with other independent, not CMB observation, which by itself is quite important. Still, we have to wait. So the setting of my talk, I will assume that future experiment observations may be related to discovery of supersymmetry. Anticipating such discovery, one can use the framework of D equals 4 effective supergravity, and if possible, derive it from 11 or 10-dimensional M or string theory. There are crucial future data for fundamental physics in this context. The first is the scale of gravitino mass. Gravitino could be the lightest supersymmetric particle and may form dark matter, and some people like this idea. Could be 1 TeV, and it could be extremely heavy. And the second set of data, which we will have eventually, is with regard to detection or non-detection of B modes, which are gravity waves from inflation. So the crucial parameter R is the ratio of tensor modes to scalar modes of perturbation, and the current bound is less than 0.3. By 2011, it will be either detection or the bound at this scale, and it will take much more time to go one order below. And I'd like to stress that one has to work with closed and perhaps open strings also, and derive the effective 4-dimensional supergravity and make prediction in this context. So in supersymmetric gauge theory, limit of supergravity, we send the Newton constant to 0 and Planck to infinity, so we have no gravitino and no gravity waves. But we already have analogous experience with the positive cosmological constant, in particular explanation of dark energy, where such limit is not acceptable. It is easy to get a positive energy Fayet-Lopoulos term in supersymmetric gauge theory. It is somewhat more complicated in supergravity, and it is practically impossible, from all I know, in effective 4-dimensional supergravity derived from M string theory by compactification. And this was stressed in our paper with Kachru, Linde, McAllister, Maldacino, and Trivedi, that the energy which we can add with help of anti-branes or fluxes on branes has typical dependence of inverse volume of extra dimensions, and it is not a constant, therefore. So one can also consider consistent modular-dependent D terms in supergravity, in effective supergravity, which will give constant positive energy, but only after modular stabilization. And after our original proposal, there was a lot of recent work which has shown how non-trivial to get this relation. So in supersymmetric gauge theory, there is no problem with positive energy via Fayet-Lopoulos. However, if you decouple string theory, open string theory from closed string theory, it is not helpful for gravitino and cosmology because gravity effects are crucial. So in the era of precision cosmology, a clear identification of Planck mass and string mass length is required. In gravity, we often use the so-called old Planckian mass, which is inverse of square root of Newton coupling, which is proportional to 10 to the 19 GeV. And in supergravity, it was more often used the square of 8 pi, a different value. And why one has to be very clear which of the two are used. You can always go from one to another, but you should not have them in one place. Here is an example. There are some observable so-called slow roll parameters in inflation, and they have to do with derivative of potential for canonical scalars, and they have m Planck squared in front of them. So the current experimental value, if I choose WMAP 3 plus Sloan digital sky survey, gives me, for combination of these parameters, the precision of the percent, and after Planck, the precision will be even better. Now assume that you are a bit sloppy about which Planck mass you are using, so you get factor of 25, which is completely unacceptable, and one has to be very careful about this by trying to do string cosmology. So the relation between Planck mass and string mass and length still has to be carefully worked out with regard to string units and translation to Planck units by the volume of compactified dimensions. And I just remind you that you can see in different places string units, either square root of alpha prime or 2 square root of alpha prime, or we have factor of 2 pi. And so in particular, if one just mixes all of these, then one can easily get the factor of 10 to the 4, which is absolutely unacceptable because we already are at precision error in cosmology. There was no good explanation of inflation in dark energy in string theory until recently. By 2003, it was realized that flux compactification and modular stabilization may support the idea of landscape of vacua. Some of them are de Sitter vacua, which could explain dark energy. For example, the simplest model of stabilization of volume of internal six-dimensional space is already helpful. Now, string theory has at least one explanation of dark energy, metastable cosmological constant with equation of state W equals -1. So far, it is in agreement with data, and no other compelling models are available to the best of my understanding. There are several models of inflation in string theory. They are flexible enough to describe the current average value of spectral index, which is 0.95, but typically predict low level of gravitational waves, low level of non-Gaussianity, and they may explain light cosmic strings if they will be detected. Observations of gravity waves, cosmic strings, non-Gaussianity can help us to test string theory, and here in this talk I will focus on gravity waves. And I will quickly show you a few examples of string inflation models. So we can either have modular inflation where there are no brains, or we can have brain inflation where the distance between brains in Calabi Yau space often serves as an inflaton field. So a couple of examples include the example which many people have seen before, and in the throat we have D3 approaching the tip of the conifold, or this situation where D3 kind of thinks before which throat to go, and it gives additional time for inflation. Or we have a stringy version of D-term inflation, which is hybrid D3, D7 brain, and this is Eva Silverstein and collaborator Dirac-Born inflation with specific features. So let me give you an example of racetrack inflation model. It took quite a lot of people to make it, but it is extremely simple, which is one of the reasons why I'm bringing it up. Many people have seen this KKLT superpotential. So we have a constant from a flux. We have a non-perturbative correction from one kind of Gaussian condensation, one more. And we have an extremely simple Kähler potential for just one Kähler modulus, which is a volume. Then we have to do this uplifting trick, otherwise we don't have a positive cosmological constant. And here we are, but it requires fine-tuning. So those are KKLT minima, but in the beginning the system was at this saddle point, spent some time here, produced eternal inflation actually, and then waterfall down to one of the stable de Sitter minima, which is the world we see today. This was not a very realistic model in the context of string theory, so we checked that in fact one can use the model which string theorists know very well, which has, after some work, just two parameters. And the facts are, you do numerical calculation, and you find in this model practically the same as in the simplest story, which says this model has no cosmic string, the spectral index is 0.95 in a very good agreement with the current data, and predicts no detection of gravity waves. Another class of interesting inflationary models, they're also modular inflation, is with regard to large volume compactification based on some theoretical work. And there are a couple of models of inflation which have been studied. And so they have less fine-tuning, but they start at least with 3 moduli, therefore have more parameters. So roughly speaking, you trade number of parameters for amount of fine-tuning. And the prediction is also very good with regard to the data. And again, no cosmic strings and no gravity waves. At present, all known brane inflation models and modular inflation models in string theory predict a non-detectable level of tensor modes. This includes the known versions of DBI models. Inflation model could predict detectable tensor modes, but this model still has to be derived from string theory, and we are working on this. New models or new versions of known models may lead to different results, but this has to be established. In particular, EVA is working on generalization of DBI models. There are several possibilities for future. We certainly will have to fit NS because after Planck, the precision will be much better. However, we may find no tensor modes, no cosmic strings, no non-Gaussianity, kind of boring. In this situation, we already have inflation models. However, if tensor modes will be detected, this will be a great challenge for string theory, which I'll try to explain, and hopefully invite people to work on this. If cosmic strings are detected, as we have heard from Joe, this is not a problem for string theory, rather welcome, because it is a potential window into physics at string scale. Now, with regard to non-Gaussianity, some solutions may be possible. So far, we have bounds, but it was not a serious detection. So, the future with additional data will somehow connect cosmology via massive GRAVITINO to particle physics and LHC. The important new data here will be Planck plus other polarization experiment. We will know where is the mass of GRAVITINO. In particular, dark matter searches may tell us it is the lightest supersymmetric particle or not. And of course, this will be also coming from LHC. Now, I was really talking to people who make projects and experiments, and they want theoretical community to help to decide what is the most important thing here. So those are specifically designed B-mode experiments. Quad and BICEPS are already taking data. Planck, of course, the satellite, as well as IBEX, Spider, Polar Bear, are in process of construction, as well as CBT pole and ACT pole. And all of these will give us the data on B-modes, or detection or the bound, by 2011. And it is clear that the CMB pole satellite, in the best case, will be launched in 2018, but this has to be, as usual, has to be seen. So what if tensor modes are detected? The current bound on this letter R is less than 0.3 if you combine WMAP and Sloan Digital Sky Survey. What will detection mean for the fundamental physics, string theory, and supergravity is the question. And so we will know beyond the bound from 0.3 all the way to 0.1 by just 2018. This is an expectation. And by 2020, we'll go one more order. So tensor modes and GRAVITINO. If tensor modes are discovered, we actually measure Hubble constant in Planck units in the early universe. And in KKLT models of modular stabilization, there is a bound, and mass of GRAVITINO cannot be smaller than the Hubble. And since you measure Hubble, you know about GRAVITINO from cosmology, if you use this class of model. Therefore, if, for example, the 10⁻² discovery that is happening, then M3½ has to be extremely heavy. And this is not what many people like, and we don't know whether this will take place. If, however, we just assume that M3½ is in 1 TeV range, then we certainly predict undetectable level of gravity waves, of course, under condition that we are working in this class of models where this bound take place. Now, models of inflation predicting gravity wave, just field theory models, chaotic inflation and natural inflation. And the question now becomes, can we derive these models from supergravity and string theory? And one of the recent surprises for us was that it was kind of believed that after current experiments, phi to d4 is marginally ruled out. Phi squared is precisely in the middle of the data, but below, most people thought there is just almost empty space, and there is not much sense to make measurements. Now, however, you change phi squared to familiar simple model, and suddenly you see that there is a lot of range between 0.14, which is the simple chaotic models, all the way down to the next generation of experiments. And so it does make sense to look for tensor modes, even if none are found at the level of Planck, which is 0.1. And this is another example where you see that, for example, natural inflation goes all the way below the Planck level of discovery. So we would like to see the following. The goal of cosmology community for a long time was to reconstruct from the data some information of the inflationary potential. And this is still a valuable goal. However, in the context of string theory and effective n equals 1 supergravity, the goal is to get some information on Kähler potential and superpotential. And of course, most of it we would like to derive this effective n equals 1 supergravity from string theory and M theory. And so generic potential of n equals 1 supergravity depends on a number of complex scalar fields, and everybody has seen it here. So the problem was of making chaotic inflation, which is just phi squared, into supergravity comes from the Kähler potential. And the point is that with canonical Kähler potential, what you see that the potential blows up at large values of field, and slow roll inflation is impossible. So it's just too steep, no inflation, as soon as you go from phi squared to supergravity. And the solution to this problem was shift symmetry, which was discussed in Japan by this group of people, and they have presented the equally good Kähler potential which however depends on phi plus phi bar, and the superpotential which slightly breaks this shift symmetry, and the potential is very curved with respect to this field x and the real part of phi, and these fields quickly go to their minima, whereas because the Kähler potential does not depend on the difference, this is an inflaton, and the effective potential is precisely of the nature which we would like. And with all issues of quantum corrections, etc., if they discover tensor modes, this is at least the way to explain them. There was no explanation of natural inflation in supergravity, and recently when I realized that this is serious, all these peoples are going to measure, and they may find or not. So I wanted to make a progress with implementing natural inflation first in supergravity and then try to derive it from string theory. And here is a story. It is surprisingly simple. You just take a quadratic shift symmetric Kähler for one complex field. You have this same familiar superpotential. We know how it comes out. And then you have to do again the uplifting thing, because what you find afterwards, that there is a minimum at some value of the radial variable, and the radial direction is extremely steep. And at this minimum, the potential is that of natural inflation. So this is a picture which shows you that there is a very sharp minimum in radial direction, an extremely shallow minimum for the axion in this range. On the other hand, if you take a much longer range, this potential shows a periodic structure, which is exactly the feature of natural inflation. So natural inflation potential is a slice at the bottom of the valley of this supergravity potential. And of course, if they discover those gravity waves, we would like to have something. So we conclude that there are models of inflation in effective four-dimensional supergravity which predict zero tensor modes, all the range from the current bound to the level of detection which people hope to go by 2020. In all known cases, they have this particular feature, shift symmetric quadratic Kähler potentials. And we may have to wait at least till the first range before we know if such models are valid. And of course, we anticipate learning new things about supersymmetry at that time, which perhaps will tell us whether we want to think in terms of Kähler potentials and superpotential or not. Now, in string theory, the computable Kähler potential in known cases of Calabi Yau compactification always have shift symmetry. However, they're logarithmic, as most people in this room know. This is the standard Kähler potential. If we start with n equals 2 supergravity, which is Calabi Yau at large volume, at large modular limit, these are intersection numbers, and shift symmetry is for free. In fact, the first time I have seen this particular Kähler potential was in the black hole paper by Ferrara, Andy, and myself. It had nothing to do with cosmology. But this is the standard. Now, if you go to the case of KKLT, which is just the simplest, this is the case when there is only C11 and it is equal to 1. And these models predict undetectably small tensor modes of inflation. And we are checking this. So we went through everything which we know, and this was each time a conclusion. And so very soon we probably will finish this investigation, and this will be, it looks like a conclusion. Now, the reason for this, the basic reason why things don't work the way we would like for tensor modes is the following. Take just one modulus, and this is the potential. So the axion is as steep as the radial modulus, and this is an abstraction to inflation model of assisted inflation in known models of superstring theory. And there are no detectable gravity waves in models with stringy logarithmic Kähler potentials of more general nature. And by the way, I'd like to tell you about my work with my former student Prakushkin, where we use supercosmology mathematics. We introduced this code for any number of moduli. So you give any Kähler, any superpotential, and you can immediately plot the potential or whatever you need. So the major question is, can we derive axion value supergravity models from string theory and predict gravity waves? Just in case, what if they discover? And so this is a work in progress. And we take into account various issues in axion physics and string theory, and concerning axion decay constant, which was discussed in these recent papers, because the whole story about detecting or not detecting gravity waves, which will cost billions of dollars, is some small numerical difference in the following parameter, in some parameter in an exponent. I'll show it later. So what we see now is that there are candidate models in type 2B orientifold with hypermultiplets which are cut down to chiral superfields by orientifolding. The simplest examples are given here, but we also would like to pursue and see if this general case recently discussed by these people, just type 2B orientifolds with hypers, may help us to go around the problem of generic Calabi Yau. And this, as a reminder, the simplest model which we'll be able to check, which I presented at one of the previous string conferences, is type 2B string theory on K3 times T2 over Z2. So a while ago, Tripathi, Trivedi, and Ferrara, Trigiante, and this group performed the stabilization of moduli in this model via fluxes. And then we found that there was some apparent abstraction to fix the remaining modulus, but we have found that there are more fermionic modes. And in the end of the day, with Paul Aspinwall, we concluded that it is a very elegant model where all moduli are stabilized. And it is this model which I would like to test first, because here we have a particular coset space. There is a very clear supergravity structure, so it is easier for me to study it. And there is in this particular case, there is a product of a volume of K3, and this has to do with these hypers associated with this coset space. And if we succeed to fix the T modulus and X0, then in principle, if the minimum is at very small values of these parameters, then we may see this kind of Kähler potential, which, by the way, immediately has the shift symmetry which is required. The main problem, of course, that it is logarithmic. And then in the paper with Aspinwall, we studied carefully the issue of instanton corrections. And in the end of the day, it is what kind of a number we can actually reach here. And the model, therefore, will either predict gravity waves or not. And at this stage, we don't know. So there are two issues with regard to most crucial future data from the perspective which I was trying to explain. To find inflationary models in string theory predicting the detectable level of B modes or prove a no-go theorem. And to relate inflationary models to particle physics via the mass of GRAVITINO in view of the bound which I discussed. So if we use for stabilization this type of models, because of this bound, the detection puts an enormously serious constraint on the mass of GRAVITINO. And so if we have the model of large volume compactification, we just learned talking to Fernando Quevedo that the bound is even more severe because the factor nu here is huge. And so if we want to see TV GRAVITINO, here we have to see TVH, Hubble constant, very unusual, or even much smaller. There is a particular model, somewhat fine-tuned, we don't like it too much, but there is no bound here. And just to show you, the usual IDS minimum is here, and here is this fine-tuned Minkowski vacuum, so that the GRAVITINO mass is completely unrelated to the Hubble. So in the context of inflation in string theory and supergravity, the detection or even non-detection of the tensor modes from inflation is of crucial importance. Of course, detection is much more interesting. At the present level of understanding, there seems to be a unique way to read the features of the Kähler potential from the sky, which means if there is no detection, then we would say Calabi Yau threefolds generic logarithmic Kähler potential have this prediction that R is much less than 10 to the minus 3, and therefore the no detection can be viewed as a prediction from this set of Calabi Yaus in the stringy landscape. On the other hand, if there is a detection, a simple way to predict it in supergravity is to use shift-symmetric quadratic Kähler potentials. And then we check that they indeed have possible gravity waves just below the bound and all the way to the detection. And the question is, are they derivable from string theory or not? And this is where our work in progress is focusing now. So the other point is that the mass of GRAVITINO is tied to future detection or non-detection of tensor modes in the most developed string theory models. And so with regard to scale of GRAVITINO mass, if supersymmetry is there in nature, it may be in the dark matter, in lightest supersymmetric particle, or 1 TeV, or 10 to the 13. So what do we know today? If they are either lightest or in 1 TeV, then we should either use the very tuned models which I showed, or we actually need new ideas here. And I think phenomenology tend to think that 1 TeV is a better expectation than the huge heavy GRAVITINO. But if it turns out the GRAVITINO are extremely heavy, then we have easy life with those inflationary models which are based on stabilization in KKLT context. In conclusion, when we learned that our universe is accelerating, it was a creative crisis which forced us to reconsider many issues in string theory, including the issue of modular stabilization and metastable vacua. And we have recently seen so many interesting metastable vacua construction in gauge theory. It all came from, roughly speaking, from supernova. If tensor modes are found, this may be equally important. It may provide us with information about the Kähler potential and force us to consider pseudo-phenomenology with super heavy GRAVITINO or invent new methods of modular stabilization. Thank you.
Other questions? comments? Yeah.
Renata, as you know very well, the usual obstruction to getting a significant tensor perturbation can be phrased by saying that in such models, the inflaton would have to have a total excursion which is bigger than Planck's scale.
Yes.
Now, the usual worry with trying to get such a model out is that if you leave out some corrections, since you have to control the potential over such a large range, those corrections would then ruin the flatness. So
yes.
I'm sure you're thinking about it.
I certainly, we were thinking about this. And indeed, one of the main expectations that tensor modes will never be found is that you need, starting with the simplest version of Linde's chaotic inflation, the range of waves of Planckian scale and more. And some group of people says you should not see it because you have no control over quantum corrections. But those people, they're looking at the sky, and they may find it. And therefore, if this will happen, and again, what impressed me mostly that after the first range, after Planck stops and tells us we don't see anything as well as the rest, it will be another range where still the detection may take place. And so, if this will happen, we will say this effective supergravity. You are afraid of Planckian scale waves in quantum field theory. What is effective supergravity? What is the real nature of M and string theory? We simply don't know. And this is what I was trying to say, that the information from the sky will tell us in the end of the day. And if it would be completely hopeless to detect those waves, we would not see all the people looking and making this experiment. So we just have to think more about it, I believe.
Are there further questions?
Here.
So in one of your transparency, you said that for Calabi Yau compactification, Kähler potential has a shift symmetry. But if I understand it correctly, that's for large volume limit of Calabi Yau.
Yes.
So are you assuming that the modular is stabilized?
Yes.
For large volume?
This is very, very good question, because in this paper with Shamit and with students, we are looking at modular stabilization in the deep interior of modular space, indeed. And there, no such things are happening. We have completely different situation. However, in the end of the day, what we need to compare anything we find from string theory with observations. I need a four-dimensional space-time because so far this is a setting for standard cosmological model. So unless I can derive effective supergravity, I have no way to make a prediction at this stage. And unless somebody tells me what to do, if something happens deep in the interior of modular space, that is precisely the conceptual issue here. And it is an invitation to string community to think more, because indeed those scalars are coming out only in the limit of large moduli. But if you are not there, you don't have effective way to compare with the data.
Okay, then let's thank Renata again.